data into the higher and higher memory locations. So it is basically, it will keep on growing. The stack is keep on growing actually, if you keep more number of books on top of each other. So instead of books, these are data in the memory location, in the RAM memory location. And pop is exactly opposite. So let's say you have stored up to 5 data on top of each other. That means these are different data values, so which are kept in subsequent memory location in the increasing order. So lowest one is having smallest location address, and this one is having +5 from the lowest one in this case. And now if I give pop, so then the top of the stack, basically the stack pointer will always point to the highest position, okay, at any point. So every push instruction, stack pointer is pointing to the higher and higher position by one step, one memory location higher up. So now if you start giving pop instruction after this 5th push instruction, so then the top of stacks, that means whichever is on the top of this particular stack of data space or this memory location, so that will come out, okay, and then stack pointer will decrease by 1, so that means it will come to 4. And next time you give pop, then it will actually take out the topmost one, and then it will come down to the lower one, and then next time it will again do the same thing. It will keep on doing the same thing until the pop actually gives the first location. That means if you give 5 push instructions, you must have 5 pop instructions at some point later on in the program. If you give 2 push instructions, you cannot give 3 pop instructions. Okay, so that is not allowed. So the total number of push instructions that you are applying in a program, that must be accompanied with same number of pop instructions subsequently. Okay, so this is a sort of a rule in programming, you can say, because otherwise you can actually keep on losing the data if you have unequal number of push and pop instructions. So that means one push should be followed by 1 pop instructions. If you are applying 2 push instructions, then 2 pop instructions should come, and so on. Okay, so we'll see with examples as we go to programming. XCH a comma byte. Okay, so this is the next instruction. This is an exchange instruction, which actually talks about the exchange of data, 8-bit data with accumulator. Okay, so this can be done with 3 addressing mode, so direct, indirect, and register. Basically, this byte could be 8-bit address. This byte could be 8-bit some pointing by using R0 or R1 or any other registers, and also it can be any register. For example, this byte could be exchange A comma B. Okay, so that is a register addressing mode. So that means this exchange will happen between 2 8-bit data, and one of the exchange location is accumulated. And this is 8-bit because it's a byte exchange. Now we can also do in 8051 the 4-bit exchange. For example, exchange of lower nibble. So only lower nibble is allowed over here. No higher nibble is allowed. What is a nibble? Nibble is a 4-bit chunk within a byte. So that means if you split a byte into 2 parts, left-hand side nibble and right-hand side nibble, you can say, or the higher nibble or lower nibble. Okay, so here it is about lower nibble. So that means the D3 to D0 bits of accumulator will get exchanged with address at RI. Now look at one thing. So whenever you see RI means that means you can only refer to R0 and R1. Okay, so this is a sort of a rule that you must remember. Wherever you find RN in certain other instructions, you must have seen, so that RN indicates R0 to R7, but RI means R0 and R1 only, any one of those two. And here it is said that address at R0 or R1 should be used to point out some memory location in the RAM space, and then it takes the data, no lower nibble data, that is lower 4 bits, and then exchange with the lower 4 bits of accumulator. So that is XCHD. Now you can have a question in mind, why they are actually suddenly doing 4 bits instead of 8 bits. Okay, so 8 bits makes sense actually more than doing something with 4-bit exchange. So this is basically done to manipulate a BCD kind of numbers, as we had seen with decimal adjust accumulator DAA instruction earlier. So where the nibble level operation was done, and also for the swap instruction was there, one of the instructions that we had seen earlier, SWAP. So where two nibbles, upper and lower nibbles, get exchanged with each other. Okay, so this kind of nibble level operations are mainly meant for BCD or binary coded decimal kind of operation. Okay, so there are some examples you can actually see over here that they are doing some shifting of BCD number. These are some examples. You can look at it. Just whenever you come across a program, so that means this is a small program they have written as an example. And whenever you see this program, you can always look back to the definition which is given up higher up in the tables, other tables earlier that we already discussed. And then you can see basically this is the immediate data. So although hash is not written over here, but preferably hash should be written. It depends on assembler again. Sometimes our compilers and assemblers are intelligent enough to find out the difference, whether you should consider a hash over here or consider @ symbol, like address @ symbol. Okay, @ means address, and hash means data. So you can look at this example. So we can see this. We'll cover the other instructions first, then we'll come to programs. Okay, now there are some instructions in 8051 which are related to external RAM memory space. External RAM is the external data memory space, because RAM is a read-write memory. You can always write and read as many number of times as you want. So external RAM means something which is beyond 128 bytes of RAM, internal RAM. So internally, 8051 has 128 bytes of RAM. Externally, you can connect up to 64 kilobytes of RAM, because you have 16 address lines, and that is why you can access external RAM, and there are instructions for accessing that external space. Why there are instructions? Because it actually makes it very efficient, or relatively efficient, as compared to using simple move instructions while taking or exchanging data. So whenever you come across move X, okay, so earlier we have seen only MOV instruction, but now it is X is also there, move X. So whenever you find X instruction, that means it is related to external RAM. Now, whenever this move X instruction comes, obviously your EA bar, your PSEN and other signals read write bar will get adjusted automatically by the timing and control unit. So this is basically telling the hardware by using this X symbol that I'm accessing RAM. So don't read or write anything, or don't try to read or write anything from the code memory space, because code memory or program memory can be another 64 kilobytes space. So MOVEX a comma @RI. So as you have seen by now that in all the instructions, if a mnemonic is followed by some operand, that means that operand, the first, if there are two operands, then the first one is the destination and the second one is the source. Okay, so that is a sort of a rule of thumb in case of 8051 and many other microcontrollers. So MOVEX a comma @RI. RI, as I said, RI, whenever you come across, I means R0 or 1. Okay, and if it is Rn, it will be R0 to R7, any one of those 8. But Ri is given, that means only R0 and R1 are allowed over here. @, that means the address is specified at that R0 or R1 register. So whatever address is given in R0 or R1, so that data memory space, that means 8-bit address is given, right? R0 and R1 are 8-bit. So 8-bit address is given. So whatever data is stored in the memory location pointed by that 8-bit address is coming to A. Okay. Now the point is, obviously, due to, if the address is 8-bit, your addressing range is only up to 256 locations, memory locations. So you have a limited memory locations. You cannot go to enter 64 kilobyte space by using this MOVEX a comma @RI. Okay, so only limitation is up to 256 memory locations can be addressed, because Ri itself is 8-bit, so 2 to the power 8 is 256. So that's how I'm understanding that it should only get to address 256 bytes, and that to the first 256 bytes in the memory location, which is external, outside the chip, outside the microcontroller. Just opposite to this first instruction is movex @ri, comma a. That means whatever value is stored in accumulator, that gets copied to an external RAM memory space, and the address of that RAM memory space is specified by the content or the value inside R0 or R1. So R0 and R1 is containing the address of an external memory space within the first 256 bytes of external memory or RAM, and that space gets copied from A, the value of A. Now, it might be required that since your total external RAM is 256, it's not 256, it is 64 kilobyte. Right? So if it is 64 kilobyte, that means you must have some instruction, and that's what we can access all 64 kilobyte by using these two instructions, the last two instructions. So here it is given as the first instruction, movex a comma @dptr. So that means move the content from the external memory location addressed or pointed by data pointer, which is a 16-bit register, and that means 16-bit address is stored in data pointer, and data pointer has DPH and DPL. There are two parts in data pointer. So this total 16-bit data inside data pointer is now an address for an external memory location or in the RAM space, and that address actually comes to the data, and basically it comes to the address bus of the microcontroller, and then it reads that value inside that address and then copies it, brings it to the accumulator inside the microcontroller. That means some 8-bit data, it is copying 8-bit data, but the address is 16-bit over here. In the previous case, the data was 16-bit because accumulator is accumulator is 8-bit and Ri is also 8-bit. So you're copying 8-bit value from one memory location to accumulator, but address is also 8-bit. So that means data and address both are 8 bits in the first two instructions in this case. Whereas here the address is 16-bit pointed by data pointer, but data that is coming is only 8 bits. So same thing in the opposite direction. So you can copy the content of accumulator into the external memory location whose address is given by data pointer. So data pointer value comes in the address line. Okay, so these two instructions are actually the lower two instructions are more commonly used in real practice if you at all having an external RAM connected to the microcontroller. So these instructions, these all four instructions are valid if you have an external RAM connected, physically connected to the microcontroller. If you don't use that external chip, then these instructions are not used at all. Then simple move instructions are good enough. Look at another just observe, apart from A, there is no other register. So you cannot do this with B register, you cannot do this with SCON, TCON, and any other register. It is only one and only A accumulator register which gets data to and from the external memory. So this is a limitation also of this type of instructions. Okay, so then there is another other two instructions. So instead of external memory space in the RAM, you can also access in external memory space in the program memory. Okay, so here the instructions are written as move C. So data transfer instructions from external code space. Now the point is, the program memory should not be updated in real time. So you cannot write to the program memory or code memory. So it must be written once at the beginning. Okay, so you cannot write to it every time when you want. So that means during runtime or during normal operation, you can only read the instructions or data from the code memory space or the program memory space. Okay, so that's why there are only two instructions. There is no write category instruction into the code space, but only read category instruction. Look at this, both are read instructions. So read from program memory. So first one, move C a comma at the rate a plus dptr. So that means move 8-bit data into accumulator from the code memory space, but the address from where the data should come depends on the value of data pointer and the value of a. Okay, so first it does this thing. Whenever you apply this first instruction, move C a comma at the rate a plus dptr, you can think of a bracket after this at the rate sign, bracket open and bracket close over here. So that means the value of accumulator gets added with the value of dptr. Now dptr is a 16-bit value, accumulator is a 8-bit value. Now this 8-bit plus 16-bit, they gets added up. Obviously your result should not overflow beyond 16-bit. Okay, that is another consideration here. Your result of the addition of dptr value, 16-bit value plus 8-bit value in accumulator should not beyond 16-bit. So the result of this addition must also be 16-bit, preferably, for accuracy. Basically, we have to make sure through our programming that the value should not go beyond if after addition. If is the maximum value within a 16-bit space or 16-bit address width, because your microcontroller is having 16-bit address lines. So your address is a sum total of dptr plus accumulator, but that sum should be again 16-bit, and whatever the final value comes after this addition, accumulator plus dptr, acts like an address value which comes to the address line of the microcontroller. Then that address will point out to some location in the program memory, and that value in the program memory, which is pointed by this address, comes to accumulator. You can see there are 2 or 3 steps happening in one instruction. So that's why RISC at that time, while 8051 came, RISC was not actually present at all. So there was some conceptual framework, but obviously there was no RISC processor. So in 8051, they were trying to squeeze as many functions as possible through instructions. That means one instruction is serving multiple purposes. Okay, so it is doing some addition, it is providing address, and then it will doing the copy, and whenever the C thing comes, when automatically your program store enable signal will get basically activated, so that your external flash memory or external EEPROM or external EPROM gets read. Okay, so you read this data to accumulator. The second instruction is actually the same thing. So except dptr, it is program counter. So the value of accumulator gets added to the value of program counter. So 16-bit program counter value plus 8-bit accumulator value gets added, and the final addition should be less than 16-bit value, should be within 16-bit, that is FFFF or lower, and then that value is taken as an address, and then that address is pointed to the program memory space, and the value at that address comes to accumulator. That's a simple. So why they are given move X and move C instructions? Because you can easily discriminate. So without much hardware overhead, you can automatically discriminate just by issuing the right instructions between the data and code memory space. Now, another important type of instruction is Boolean instructions. Boolean instruction means bit level instructions. So everything is happening with respect to single bit. So in 8051, we have seen certain registers are bit addressable. So you can see this SFR, special function registers. Some registers are bit addressable, whereas some other registers are not bit addressable. They are byte addressable. Okay, so whatever comes under this column of bit addressable, so like BA, PSW, IP, and all those things. So this registers are some of the most frequently used registers. Okay, and this registers are also bit addressable, as it is said, and bit addressable is possible through certain special group of instructions, that is Boolean instructions. So these Boolean instructions are actually very often used in 8051 because of its flexibility. You don't have to deal with all 8 bits together or 16 bits. So generally these are all 8-bit registers. There is no 16-bit as such, unless you combine them or concatenate them separately. So bit level operations are available for ending like ANL C comma bit. So C is the carry flag here. Okay. So where is C? C is present in program status word. Okay. In PSW or flag register, as I said earlier, so there is a carry bit. And that carry bit basically gets updated if you are doing addition or subtraction. So carry bit gets updated with borrow value if it is subtraction instruction coming before, or it is carry for simple addition, and also for other rotate instructions. So this carry bit gets affected. You have seen that earlier if you have revised. So carry bit is, again, it's like an accumulator like bit. So basically in accumulator is a 8-bit register. Obviously carry is a single bit out of those 8 bits available in PSW, and carry bit is one of the most important bits where you can perform ending operation ANL, so which is C comma bits. And now the bit means you are giving an address of any one of the bits from the bit addressable RAM. So within the bit addressable RAM, this bit could be any bit from any of the uh, allowed registers. For example, any bit from B, any bit from A, any bit from even PSW. So C is present within PSW, or any bit from any one of this particular group of IP, P3, basically all ports, port 0, 1, 2, 3. Then interrupt registers like interrupt priority and interrupt enable, IP and IE, then serial control, and then timer control. Okay, so this registers, any bit from any one of these registers could be the bit over here. Okay, and now there is another instruction which is ANLC comma bit bar. That means it first actually complements the bit. So it's basically it's a complementing the bit or inverting the bit by using a NOT operation, and then doing the ending operation. Similar to AND, so there are two OR instructions. So ORL C comma bit, that means C gets ORed with another bit from the bit addressable space. And look at one thing that in every cases the result of ending or ORing is coming on the C register. That means carry gets updated with the result of ending or ORing. So ORL C comma bit bar is there. Now, apart from logical, we can also move something to C bit, like any bit to carry bit, or the carry bit to any other bit within the bit addressable RAM. So this is just copying the bit from one location to another location without affecting other bits in the same register wherever you're putting this, you're pointing as a bit over here. Now there is clear bit, so that means you are clearing the bit, any bit within the bit addressable space. Similarly, clear carry is there. Set B bit is basically you are setting it to 1, any of the bits, or set B carry, that means you're putting carry equal to 1. So that means you can initialize a carry bit to 0 or 1, or you can also initialize any other bit within the bit addressable RAM to 0 or 1. Then CPLC is a complement C, that means it is doing NOT operation on C and then updating result into C. Just it's inverting the value of C. CPL bit is equivalent to you are NOTing any bit, that means you're inverting any bit and then updating that bit. Now, the remaining instructions are actually branching instructions. That means there are instructions which works on conditions. Okay, so these are conditional instructions. So all J related instructions are conditional. Now we are actually jumping to the last few instructions, even beyond this list, where we will mostly look at some sort of jumping or branching. So jumping or branching means you are executing a sequence of code in the program memory, and then you are suddenly changing the codes. That means you are actually going to drastically different memory location in order to start with the subroutine, or in order to basically add execute a subprogram, so or even interrupt subroutine. So for those kind of instructions we generally need to branch. So we have to, let's say, jump to a drastically different location which is far off from the present location. So that present location may be anywhere within that 64 kilobyte space. So you can do jumping or branching in the backward direction. You can do jumping or branching in the forward direction. Means that means you are from lower memory location to higher memory location you can jump or branch, or alternately if you are at higher memory location then you can branch back to the lower memory locations. So these are all possible. So this is an introduction before I started with this branching or jumping kind of instructions. And in addition to jumping or branching, so these are conditional branching or conditional jumping instructions. So conditional means it actually looks at certain conditions, basically some parameters, some values, and then it takes the decision automatically whether it should really need to it, whether it should jump or not. Okay, so now let's look at the first one. So JC rel. Rel is, the meaning of rel is a relative addressing mode. Okay, so or the relative address is given. Relative means basically either minus 128 or plus 127. See, that means or it may be 16-bit counterpart if it is a relative addressing scheme over here. So here the operand is relative, means I can relatively jump. So that means I'm asked to jump 100 locations in the higher memory location, or I am asked to move or jump to the 20 locations in the lower memory location. That means I want the memory wherever this JC rel instruction is given. So it must be associated with some address in the memory, code memory or program memory, and that from that address it can jump in the forward direction, basically higher memory location, or the lower memory location in the backward direction. So assuming my lower memory location in the upper side and higher memory location in the lower side. So one second. Just a moment. So while jumping is happening, so assuming I have some this kind of hardware connection. So always, as I said, embedded engineers should always think of hardware while writing software. So that is something you must always remember and acquire the skill, that how the hardware must be functioning, what signals are coming with every instruction. So some instructions may control the hardware lines, some instruction doesn't have any control on the hardware lines. Okay, so you have to see. So wherever you give the jump, so that means the program counter should get updated, and then it should give out some address value, and then it should give out some ALE pulse and so on. So those kind of signals must always be considered, and from looking at every instruction you can do this mental exercise, that whether that particular instruction is affecting the address data lines and the control lines or not. Okay, so you have to think from the hardware interfacing side, also inside the microcontroller, what are the blocks that get affected by each and every instruction. You can do this mental exercise as a practice. Although that is not useful for any exam, but it is useful as a skill, your lifetime skill for dealing with any microcontroller in the future. Okay, so don't think that 8051 is the end. Obviously our syllabus is covering 8051 in detail, but this is the practice session for you to gear you up for any complex microcontroller or processor or any other neural processor or any other thing that comes in the future or even presently. So whenever you give a JC some bit or relative address, so that means whatever address that is coming over here, so that is controlled from the program counter, right, inside the microcontroller. So that program counter is getting updated with the relative address with respect to the present address. So let's say JC comes at some memory location in between, and then you can actually from the relative address, that means it will jump backward or forward as per the value of this relative value. Okay, and this is basically a 2-byte instruction. Sorry, it's a 2-byte instruction, and it takes 24 clock cycles because the relative is a typically 8-bit relative value. So jump if carry relative, and just opposite to it, jump if not carry relative. So that means if carry equal to 1, then it will jump or then it will branch. That means that relative address will get either added or subtracted from the program counter value. Now, how do we determine whether it will be added or subtracted? Because if while considering this real number, that means real is indicating 8-bit operand. Okay, 8-bit operands. Here the mnemonic or the opcode should come for JC, and this REL is a 8-bit value, so which is taking 2 memory bytes in the program memory space. Now, REL value only take the REL value in the signed format. Okay, now think of a signed number, signed binary number. What is a signed binary number? Just a recap. Signed binary number means the most significant bit represents the sign of the for the remaining 7-bit value. So 8-bit number, I'm taking the most significant bit, that means D7 bit, and if D7 bit is 0, my number is positive number. That means whatever remaining 7 bits D6 to D0 is representing, that is a plus that number. And if D7 is 1, that means it's a negative number. That means minus value should come considered, and then REL, the remaining are D6 to D0 consisting of the 7-bit number. So that's why REL represents minus 120 and plus 127. Yeah, question? Okay. Okay. So jump if carry to minus 128 or plus 127 depends on the sign, and jump if not carry. Same thing, jump with bit. So you can check any bit within the bit addressable RAM, and then jump to the relative location. And jump if not bit. So it's same as JC and JNC, except it can be any other bit apart from carry. And JBC is just another instruction, which means jump if bit equal to 1 and then clear the bit. So suppose you are checking a bit, and that bit, if that is bit is 1, then jump to relative location, relative address location, and then clear the bit. So JB means jump if bit and then clear the bit. It's not carrying, it's clear the bit. Okay, so clear the bit after or before doing the jump operation. So it's a 2-step instruction. Now, question: why relative addressing mode is important? Why it is given? Why not exact addresses can be used? Yes, exact address can be used, but not with this category of instructions. But relative addressing is useful because at that time, while in 1970s, while 8050 was designed, these instructions were actually thought of. That time, people were also designing operating systems, although it was not used that commonly in microcontrollers or processors. But operating system was also getting evolved at that same time. So people were discussing that if I copy a code and then put it into another computer, another microcontroller, and that same microcontroller, the second microcontroller may have a different set of codes, and out of that my code, whatever I'm copying, is one of the codes. Something like, if I have a computer, I'm installing MATLAB, and then I'm deleting another software, making some space, and also again installing another software, SolidWorks, and so on. So what I'm doing, my MATLAB, SolidWorks are same, but my computers are different, right? So at each of one of us are having different personal computers, and each computer is having different memory sizes, different sequence of installation. Like I have installed, let's say, MATLAB first, then SolidWorks. Some other guy will install SolidWorks first, then MATLAB. So what is the problem over here? The problem is the amount of memory from the starting location gets changed for the second location, for the second software. That means if I keep on installing the software, so the starting location for every software that I'm installing is different for each one of us. Whereas once I start the software, I don't see any difference in the MATLAB or SolidWorks. So what I'm trying to say is that due to relative addressing mode, it is possible, because wherever I store, so the jumping is always relative. That means I don't have to care about the absolute address value. I don't have to calculate absolute address value while installing or copying the code from one computer to another. So that is the main purpose of relative. But at that time, relative was only 128 bytes minus side and plus 127 plus side. That is 256, actually 255 locations can be addressed by this relative. But today it is in gigabytes. So that is the only difference. With ARM also same thing, it is in gigabytes actually. Now, actually, I'll go to the next set. Actually, this is not addressing mode to my view. I will call it, these are different types of operands. So addressing modes, as I said, those direct, indirect, and all those things. But it is a combination of addressing modes and different types of operands, they are saying. We'll come to this one. So look at this. One of the ways to express operand is relative addressing, or relative address of the for the operand. Okay, so the whatever JC, rel, and all those things we have studied in just now, so those are representing only relative. But look at this, your address, instead of relative, it could be either a single bit direct, or operand could be a single bit, as we have seen. Operand could be 11 bits. Now this is a strange thing. So there are certain instructions in 8051 for branching and those jumping instructions, where the address is, instead of 16, it is only 11 bits. Why it is so? Because it can address up to 2 kilobyte of memory space. Okay, so by using this 11 bits, you are actually saving certain space in the code memory or program memory. So that is basically the main reason. And another reason is that this 2 kilobyte RAM and EEPROM chips were very, very common at that time, and were considered to be state of the art kind of thing during that time. So people thought that this ADDR11 is one of the good options. That means it will access only up to 2 kilobytes. That means 11 address lines will be used. Okay, and other address line like A12 to A15 could be used for other purposes. So that was the objective behind this. So address could be 16-bit as well. So this is very common. So this is used for certain instructions that we'll see soon, very soon. And your data could be either 16-bit data or 8-bit data. And as you have seen, this address at RI, as we discussed, RI indicates R0 and R1, and address at those registers R0 and R1, that means you can only have 8-bit internal addressing, that is up to 255 locations, or 0 to 255, that is 256 locations. or you can give a direct address, which is 8-bit direct address of internal RAM pointing to internal RAM or SFR, or even external memory also, as is discussed in MOVX instruction. And then Rn means wherever Rn, you mean R0 to R7. Okay, so in the next set of instructions, we will talk mainly about this address 16, address 11, and REL. So these three things we will be considering in the next few instructions. You have already seen the other applications, other types so far. So address 11, address 16, and REL will be more commonly used. So you have to digest the fact about REL very well. Also the purpose of 11, address 11. Okay. So there are basically jump instructions. So this JMP is simple jump instruction. This is an unconditional jump. So in the previous case, JC, jump if carry, jump if bit, jump if not carry, jump if not bit. So those are conditional jump instructions or conditional branching instructions. Whereas there are unconditional jump also. That means it is not looking at any condition. It is not checking any bit or byte or any value. Simply jumping to a direct look address. That means 16-bit address must be here, and it will simply jump to that location, and it will take 24 clock cycles. Now, unconditional jumping could also be possible by doing the addition between the 16-bit value in DPTR with the 16 value in accumulator, provided you are not allowing it to overflow. So that you have to take care as a programmer that the total value should preferably not go beyond FFFF. That means it should not roll back towards lower value, because the 17-bit, if carry gets generated, that carry is ignored over here. So only lower 16 bits will be considered after addition. Okay, so this is unconditional jump, but where accumulator is also involved. So address is the sum total of accumulator plus data pointer, whereas here the address is direct addressing. Okay, and then there is unconditional call instruction. Now, call and jump both are branching instructions. So these concepts that I'm covering, these are also true for ARM processor and other high-end processors. Okay, only the terms are defined, instructions are more powerful, they will do more than 2 or 3 operations per instruction. So those complexity will be there in higher order or more advanced microcontrollers. But the basics are the same. It's so interesting that whatever basics people developed with 8051 and 8085 like processors or microcontrollers back in 70s are still today valid, except they are adding more and more jewelry to it, making it more glittery and more powerful, more user friendly, less time consuming, less power consuming. So those are things we are doing since decades. But this innovation was originally done in 1970s, and that's why basics are so important. So I'm just trying to say that this call and jump are different types of branching instructions, where call and jump are pretty similar, except the call actually saves certain information before doing the branching, whereas jump will simply change the program counter. So jump address means what? This address comes to the program counter. So that means I'm doing a jumping. So that means program counter is providing the address for the memory location in the code memory space or the program memory. And whenever I issue this kind of JMP address, 16-bit address, that means the 16-bit value simply gets copied to program counter. That's all it is doing. It is not doing anything else actually. The effect is jumping action. That means program counter was having some value, and then suddenly I'm giving a drastically different value or any value within the 64 kilobytes of memory. Okay, and same thing over here. So whatever it is finding after doing this addition, a plus dptr, it gets copied into program counter, and that's why it is acting as an address. So call address is same as jump address. So that means except some differences. So call address is also copying this address value, 16-bit address value, into the program counter. But call instruction, in addition, applies some sort of push instruction in the background. So as you have seen, push is having increment, stack pointer, and so on, move something in the background, push and pop instructions. Similarly, call instruction is actually applying a push instruction. So that means it will push the program counter to the top of stack. So call instruction, basically whenever you invoke or you give this instruction, call 16-bit address, before copying this address into program counter, first it will copy those 16-bit values. So program counter is a 16-bit register. So it has two 8-bit chunks basically. So it will take two 8-bit chunks of data or bytes and then store into the top of stack. That means it will increase stack pointer by one, put program counter one of the bytes, and then it will again increase stack pointer second time, again put the other 8 bits from program counter into the top of stack. Okay, so that is call instruction. So call instruction is having a in background two push instructions, and then it copies the value of address into the program counter. So this is basically the application of this kind of, or rather, this is the purpose of this call instruction. Now, why do we need call instruction? What is the application of call instruction? This is to call a subroutine. So suppose I want to call a subroutine, then it will, I need to go to different address, starting address location for the subroutine, which is given call address. So ADDR is the starting address location of a subroutine. Now, once the subroutine is called, so it should remember, the processor should remember where to come back after the subroutine execution is done. So in order to come back to the location where it was executing the code, it will have to save the value of program counter. And program counter is a 2-byte, basically 16 bits. So it will have to invoke two push instructions in the background. So program counter is saved. Now you update this address into program counter, and then you go to the, automatically your program jumps, or rather goes to the starting address location of the subroutine. Now subroutine gets basically executed, and then after some time, at the end of the subroutine, you have to use this kind of RET instruction. This is return instruction. So return instruction is applying two pop instructions in the background. So as I said, call was giving two push instruction, and number of push should be same as number of call, number of pop. Okay, number of push should be equivalent to number of pop instructions subsequently in the program. So you have called a subroutine, you have executed subroutine. At the end of the subroutine, you should provide a RET instruction. So whenever you put RET instruction, it will simply pop 2 times and update the program counter from where this call instruction was given. In fact, the next instruction, next address of this call instruction. So whenever you give RET, so the value of the program counter comes to the from the top of stack to the program counter. So automatically the program counter, the program gets back to the original code by using this RET instruction. So call and RET, these are both unconditional branching instructions. Okay, as the JMP instruction. So there is no if carry or if not carry. So those kind of conditions are not there. So it is simply calling and returning from the location. So now RETI instruction, so it is a return from interrupt. So there's a slight difference between RET and RETI. So RETI basically return from interrupt means what? So interrupt service routine is there. So interrupt service routine is a subroutine, obviously. So it's a type of subroutine which may come at any time. Now interrupt can invoke an instruction equivalent to call anytime without even writing this call instruction. So what I'm saying, that call address is a deliberately written instruction. I want to call a subroutine under at certain point in the program, then I'll write call. But interrupt can come anytime. You may not have a call instruction at that time. Interrupt are asynchronous in time. That means it can come at any point of time, wherever the code might be. So whenever interrupt comes, so similar pop kind of operation, two pop operation for program counter in the background will automatically get invoked. So that is how the interrupt block in the microcontroller operates. There's a lot of automation which goes on in the background by timing and control unit. So interrupt come anytime, is coming anytime, whether it is hardware or software. So you may not have the call instruction at that time. So the timing and control will automatically invoke two push instructions for saving program counter for the return location. Now, after you service the interrupt service routine, which is a type of subroutine, you apply this RETI, so automatically it will invoke the pop instructions two times. But only one thing that will do, extra thing that RETI will do, basically it will update certain flags. We'll see in interrupt registers, there are certain flags which actually gets updated by RETI automatically, that interrupt has been serviced. So that means you have done with the servicing of the interrupt routine. So that's what is updated, which is not updated in RET, simple RET instruction. So this is a slight difference over here. So only it updates certain bits. Apart from that, it also invokes two pop instructions for returning back to the original position in the code after interrupt service routine. And NOP is a simple type of delay operation. So it just wastes 12 clock cycles. So NOP is something like a delay instruction for 12 clock cycles. If you need multiple delays of 12 clock cycles, keep on applying NOP instruction, no operation instructions. So I think possibly the most simple instruction. Okay. Let's see. Okay, so we have completed this. So any question until this point? Do you have any question?
Sir?
Yeah.
Sir, you told about move X instruction and move instruction. Those are two separate instructions because move X is used to access the external memory.
Yeah.
Sir, so wouldn't that mean that we are able to access 64,128 bytes of data memory? Because at the same time, we can address the internal data memory, and at the same time, we can access external memory just by using two different instructions.
True. So actually, this is a good observation. That if you simply write move a comma address RI, it will only access the internal RAM location. But the moment you are giving move X a comma RI, it will access the external RAM location. So this X basically inhibits internal RAM and enables basically whatever signals that we had studied earlier will be utilized, like this ALE and then read write bar. So both the signals get activated for this MoveX instructions. Okay. Whereas if you simply give move instruction, obviously with the a comma RI, this external signals are not getting activated. So as a result, external memory is not accessed. So let's look at the simple move. So you can you can put the address of the internal RAM location over here. So that's why this is a generic location. Move a comma generic source, and generic means all four addressing modes are allowed over here, right? So it could be in from RI, it could be address at RI, it could be from RI. Basically, it will come under register addressing mode. Address at RI, it will come under indirect addressing mode. Okay. So these two are applicable and compatible to MoveX indirect and register addressing modes with respect to move a comma address at RI or move a comma RI kind of instruction. But whenever you give move X instruction, automatically your internal, so obviously there is internal read write signals for this all those registers, but those are disabled, and rather external read and write gets activated. So that is how it only discriminates. So this read bar and write bar signal get activated, and this ALE and all those things will come into picture. So as a result, your internal space or internal location can be ignored. So that means what I'm saying, I think your question, I'll just reiterate for others. Let me look at this instruction. So suppose Ri is having 0 0. So R0 or R1, so let's say, is having 0 0 location. Now 0 0 location is available in the internal space. Where is that? Just a moment. I'm just looking for the address space. Yeah. See, 0 0 is present in the internal RAM location, and 0 0 0 0, obviously 4 zeros, where 0 0 is also a part, is also present in the external RAM location, right? So you agree to this? Now the question someone asked, that how does it discriminate whether the 0 0 is within the internal RAM or external RAM? So the MoveX essentially disables the read write from this. So see, read write signals are going to each and every location, every memory location over here, right? Internally. So we don't get to see that in the block diagram, but it is present. I can write anything, read anything from anywhere within this 128 bytes of RAM. That includes the registers also, register banks also, and special function registers also. So this address is present at two locations. Just by issuing the right correct instruction, I am actually determining whether move a comma address Ri. So this move x comma address Ri. So these two instructions are going to discriminate whether external read write signals will be activated or internal read write. So internal, why read and write I'm saying? Because in this case, read bar signal will be activated. In the second case, write bar signal will be activated. Okay, so same thing could be possible for the internal RAM memory also. So, but any one at a time, either external RAM or internal RAM. So whether if you are applying X instruction, then obviously external. So does it answer the question?
Yes, sir. But
Okay. Okay.
Sir,
Any other
one more
question?
doubt. Yes, sir.
Yeah.
Could you please show the schematic of the microcontroller, the pinout? So my specific question is basically when I'm using MoveX command, then I am not specifying where the address locations or which pins I'm giving the address location at, right? So there must be some fixed address lines, right? I think we saw. So is that what happens?
Exactly. There are fixed address lines. Look at this. A0 to A7, which is multiplexed with port 0, port 0.0 to 0.7, and A8 to A15, which is multiplexed from port 2.0 to 2.7. So these are the fixed address lines, or multiplexed but fixed address lines for the microcontroller. So whenever you apply MoveX instruction, so how it is related to the block diagram, you have to find that link. So whenever I give a MoveX instruction, so let's say I'm issuing this instruction MoveX a comma address at R0, for example. I'm applying this read instruction from the external memory location. So R0 is present in the internal RAM. So where is the RAM? SFRs, and then this is the RAM, right? So R0 is present inside this, and R0 is a 8-bit register inside the RAM, or it's a type of special function register or some location in the RAM. So that R0 value is an 8-bit value. So what will happen? It will come and copy to this 8-bit bus. Okay, and it will come to the data bus. So actually you are transferring address to the data bus, okay, temporarily. Then it will come to the buffer, and then through the buffer it comes to the program address register. Look at this, program address register is a 8-bit register. So this is why 8-bit values are sequentially transmitted. If you have 16-bit to be transmitted, 2 times you have to do that. So in this instance, MOVEX a comma address R0, basically the value of R0 is coming over here, going through the data bus and then going through the buffer. Buffer is nothing but it is the same connection, you can say, just to prevent extra hardware loading, means extra capacitive loading. And then this data, whatever R0's value is coming and sitting over here in the program address register. Now in the program address register, from the program address register, it's an 8-bit address, okay. So that means A7 to A0. A7 to A0 is a part of port 0. So what it will do, the value of R0 is now coming, is getting copied. Basically, it's not happening in one clock cycle. First it gets copied, first it gets read, then it gets copied, obviously, at the same time. And then in subsequent clock cycle, it's coming over here, and it goes through this. So there is a tap here. It doesn't go over here because the port 2 gets disabled by the timing and control unit. So the data will continue further and come to the port 0 driver, and port 0 driver will get updated. So that means whatever address, 8-bit address from R0 came over here is now coming through the drivers. So port 0 drivers will be enabled. So those 8-bit address comes over here between A7 to A0, which are multiplexed, okay, with port 0. So the address has come over here, and apart from that, while the address is applied, after applying the address, the timing and control will release the read and write bar, which is I think where is the read write bar? It's not shown actually in this diagram.
Yeah, got that. Okay. So then the address enable and everything will happen, and now you are in a position to read or write depending on whatever you wanted to do. Correct?
Exactly.
And which port are we going to use for the actual data transfer? Port B, right?
Port for data also you have to use this port 0, because
okay. So the data will automatically get latched onto the whatever external memory I'm using, right? So you give, then you latch the data on that, and then you again use the same pins for transferring data.
Slightly different than what you said. First, we
Okay.
have to latch the address.
Yeah, that's what.
Yeah, we have to latch, not latching the data, latching the address,
latching address,
whatever.
yeah.
Whatever came from R0, that must be latched by using this ALE signal. And how can we understand this? From the timing diagram. So where is that timing diagram?
Got it.
No, I have to. So you have understood, but I have to tell it for others also. So I think it's there in the other PPT file possibly. So what is done basically, you have to first copy the address from R0 to this, and then you have to apply ALE signal. So through ALE, your data, basically this address A7 to A0 gets latched to the external latch or external 8-bit latch, and then you read the data from the same thing, and then the data will come from port 0.0, that means D7 to D0 of this port 0, and then it will again come through the same line, but it will go through this path now. Okay, instead of this was the address path because it is connected to address register. Now the data will come through the latch, it will get stored over here, and now where do we wanted to save the MOVEX a comma address at R0, right? So I want to save the data in accumulator. So the data will get latched, and then subsequent clock cycle it will be read, because at that time the accumulator may not be ready also. So assuming it's not ready, then timing and control will apply read to this latch and write to the accumulator. So MOVEX will do this thing. So whatever I just explained to you, a different sequence happens for each and every instruction, and we don't have that much time to explain and go through the instructions, but if I explain you one or two instructions very carefully, you can easily decode for every other instruction what exactly is doing, what should be the timing preferred or approximate timing, what should be the approximate flow, which lines are getting activated when. So those things are important. So I'll repeat for MOVEX a comma address array. So just very quickly, I hope it is quite clear now, but still. So RAM is having that RI or R0 register. So I want to copy that value address. I want to use that value as address. So that's why the value of R0 comes through this particular lines, and it comes over. It doesn't come to accumulator, or it doesn't go anywhere. It simply gets copied over here and comes through the buffer, and then it comes to the address register, program address register. And then through program register during subsequent clock cycles, the value comes to this port 0 drivers and simply goes out. And while it goes out, ALE signal latches that address into external latch, 8-bit latch. And once the value gets latched, subsequent clock cycle, the data comes in, and then that data comes through this same lines, external pins, and then internally it gets splitted into other bidirectional line. It comes to the latch, and once it gets latched over here, subsequent clock cycles, it actually comes to the data bus again. So this is the data bus, and it comes over here and then copies to the accumulator. Okay, so because the purpose of the instruction is some copy from external memory to the accumulator, whose address comes from RI. Okay, so same thing is happening for ANDing. So I'll just give an example from, let's say, AND or arithmetic instructions, or add instruction or something, you can say. Now look at this. For any of these instructions, whether this AND or arithmetic, because they are actually pretty similar, based on the addressing modes, the part of the data in the block diagram will also change. Okay, so these are some fine lines for very strong understanding. So based on the addressing modes, the path, basically which lines through which the data and address will move, and it will from where to where it gets transferred or copied or processed. So that depends on addressing modes. Okay, so whatever I said with MOVEX @R0, that is an indirect mode, right? That's an indirect addressing mode. For direct addressing mode, it is different. For direct addressing mode, so let's say I take the example of ANL A comma byte in direct addressing mode. So this is very interesting. If you understand for one or two, then others, every other instruction for every other addressing mode should be clear to you. This is so fundamental and basic. And it is so fundamental that even ARM concepts also depend on this same analogy. Only thing is extra fancy names like pipelining, barrel shifter, so also multiply, accumulate. So those complex terms will come. Those complex term means some additions to these basic functions. The basic functions is same. The addressing modes are again similar. I can tell you, and I can tell you, you will be observing that subsequently. So let's take direct addressing mode for AND A and some byte. So this byte could be, let's say, direct. In a direct addressing mode, how do I write this instruction? ANL A comma @ some number, or basically some number, 8-bit number, and that number is considered to be direct address. So this is a 8-bit address I'm giving. Now, whenever I give 8-bit address, it doesn't straightway go to the external RAM or ROM. It doesn't go outside the chip. It will only stay within the chip. So that means this 8-bit address must be somewhere within the internal RAM. Now, the point is, internal RAM is 128 bytes. But you have 256 possible locations that can be addressed over here by the direct addressing mode. Do you agree that internal RAM is only 128 bytes? But Up to 256 I can go over here. Let's take the simpler example. My byte value is less than 128. So again, two sub conditions are coming. So my byte value is, let's say, 120 or less than 128, anywhere. Given that statement, having said that, what will be done over here? ANL A comma byte, that 8-bit address. So that 8-bit value whose address is less than 128 is again within this RAM space. What I will do, the microcontroller basically will issue timing and control for reading that location whose byte value is given, that is whose address is given in direct addressing mode. That thing comes from RAM through this bidirectional data lines, and it comes and sits in one of the two temporary registers. In this case, it will be TMP1. So whose address move ANL A comma byte. That byte value is accessed. The data within that address in the internal space comes from RAM, comes and sitting in the TMP1 register. Now accumulator is already having something beforehand. So I'm not changing accumulator in this particular instruction. Assuming before ANL something had happened which had some value, which kept some value in the accumulator. Now accumulator's value gets copied to TMP2. It is quite intuitive here actually. Okay, so accumulator, obviously TMP1 is having the value from RAM. Accumulator should also have some value which gets copied to TMP2, temporary. So these temporary registers are written from two different location source, but the read-write signals are coming from timing and control registers. Now, as you can very easily guess over here, that these two values are coming from accumulator. Now, accumulator and the RAM through TMP1 and 2, and then timing and control issues a comment to the ALU. Now, ALU is a bunch of circuits having 8-bit adder, full adder, having full subtractor, having 8-bit ANDing, 8-bit ORing. There are multiple digital circuits within this arithmetic and logic unit. Now, this timing and control has read that through the instruction register. In fact, I'm going in a shortcut explanation. So there are more steps for the execution, fetch, decode, execution that happens in the other side, which are basically the, this program counter and all those sides. So you have to fetch the data from the ANL instruction opcode. It will, timing and control will find out that you have to activate the AND 8-bit ANDing circuit within the ALU. So once the ANDing circuit is done, so the result of ANDing comes from ALU. Then it comes to the data bus, which is actually the same data bus which is all around. Okay, so it output, ANDed output is coming from ALU, and it again rolls back, or basically flows back. It's not rolls back, flows back through this and gets updated in the accumulator. Okay, so this is what happens after fetch, decode processes. So I just explained to you what happens in the execution phase. So execution phase of every instruction are unique, but fetch and decode are pretty similar. Okay, in every microcontroller, for a given microcontroller or processor, fetch and decode are pretty much similar for most of the instructions, except some exceptions. But execution stage or execution phase involves unique steps or sequence every time. Okay, so we'll move on. So similarly, you can actually take different addressing modes and do this mental exercise of your own, and it is very logical and very easy also. It's not difficult. We've seen this Boolean instructions, and the last few instructions we'll cover. We have also finished this unconditional branching instructions or jumping and returning instructions. Okay, now some last few instructions. I think few more after this also exist. Just a few more, but those are even simpler. These are moderate level difficulty is there in this instructions. So listen carefully. JZ relative, that is jump if 0. Where is my PSW? So I want to see the program status. Well, so in the program status word, we have basically certain registers. So CY is C actually. Auxiliary carry, user flag, RS is basically register select, overflow, and parity. Remember these flags, and with respect to these flags, so we have to basically sometimes we need some of those flags in some of these instructions. Okay, it's not in the first case. So JZ jump if 0 relative. So that you must have applied prior to this instruction, before writing this instruction, you must have applied some addition, subtraction, or some sort of ending and ORing, XORing. Any arithmetical logic operation must have happened before the instruction, and the result must be there in accumulator, or if not, you have to update accumulator before this instruction. And it will keep on checking all the bits. If all the bits of accumulator are 0, then only it will jump to a relative location. And this relative location means in 8051, it is only minus 128 until plus 127. So there are total 256 locations, minus 128, then a present location, then plus 127. So there are total 256 locations represented by this relative. Okay. Now, opposite thing, jump if not 0. If the value of accumulator is having anything other than 0, it may be any other number than 0, then it will do this jumping action again with the relative address. So relative address means if you copy this code to another processor, then the relative distance in memory location is going to remain the same. Okay. So it is looking at condition if 0 or not 0. Now, more powerful instruction. Yeah, question?
Sir, rail is supplied by RI and from R0 and R1, right?
No. Rail is supplied by us. This is the second byte or the operand in the code.
Okay, so sir, it is written in the code and it is not stored in any data space.
Yes, it's not stored in RI or RN or anywhere. It is supplied by us.
Yes.
So it's a 2-byte instruction.
Yes, sir.
Okay.
Thank you, sir.
Yeah. So next is the DJNZ. DJNZ is a slightly powerful instruction and very commonly used instructions that you will see, which is decrement and jump if not 0. Look at this. There are so far you have seen some instructions having 2 steps internally, some instructions having more, 3 or so. So at least. So this is one such instruction where it will do decrement a value by basically it will do DCR1. Okay, so we have seen increase and decrease instructions earlier. So similarly, it will also do the decrease operation, and if jump if not 0. So that means it will take a byte. Obviously, it works in 2 different modes. So you can take a byte from a register, or you can give an address of the byte directly, and it will decrement that byte or the value whatever that byte is stored, and then if it is not 0, then it will jump. If it is 0, it will never jump. It will go to the next instruction. So every conditional instruction, remember another thing, if the condition is met, it will jump. If the condition is not met, then what? It will come to the next location in the memory and it will execute the next instruction after this JZ or JNZ. Same over here. If the condition is met, then only it will jump. If not, it will come to the next instruction, whatever might be the next instruction. So this is basically, it's like flowchart. If the condition is met, it will do the jumping. If that is yes condition. If the condition is not met, no condition, it will go to the next memory location and continue until some other conditional thing comes in the way. Okay. Now next instruction is CJNZ. Now CJNZ is basically compare and jump of not zero. This is basically not call. This is compare. Okay. Compare and jump if not zero. A. That means it will look at A and it will compare the byte with A, and if it is doesn't find it to be zero, then it will jump. What is the meaning of this? The meaning is that you have to basically it will do the comparison first of two values, two data. Okay, it will first, you are giving this byte value and then it will compare with accumulator. And if the after, what do you mean by compare? First of all, compare means whether they're same or not, right? Whether same or different. Now how a microcontroller finds a comparison result? It actually finds it by doing a subtraction in the background. Okay, so comparison basically, so you have a 8-bit number and the microcontroller or processor just simply subtracts the result, subtracts those two values, and it doesn't store the result. So that's the difference between subtraction and comparison in microcontrollers. So you will, it will automatically take two values wherever you want, whatever values data or we are comparing. It will do the subtraction. It will just update whether it is same or not, whether the difference is zero or not. If it is zero, that means it is same. If it is not zero, that is it is different. Whether it is larger or smaller, that is not determined. But the point is the result of that subtraction in this comparison process is not stored anywhere. Okay, so this is basically, this instruction is doing compare first, that is subtract first, and jump if not zero. Do the comparison and also check if the value is zero or not. So 0 minus 0 is 0. So if that is the true, then it will not jump. That means the CJ and Z means it will do the comparison, it will do the subtraction obviously, and then it will jump if not zero. So that means the value should be non-zero value. Then only it will go to the relative location. And this is happening comparison of accumulator with a given value. Okay, so that is what is basically jump if accumulator equal to byte. That means if the accumulator is same as the value provided over here, that means the comparison result is basically is they are equal. If A is same as byte, then comparison is equal. And if it is not zero, then only it will basically if it is same, then only it will go to the relative location. And you can, instead of accumulator, so to make it more powerful and more general purpose, they have actually supplied 8-bit data, and you can compare this with any byte value. Okay, so you can give supply 2 bytes, so that means this is a 3-byte instruction, whereas this is also a 3-byte instruction. CJNZ takes 1 byte, this byte, and then relative. And here CJNZ, and then this byte could be, look at the addressing modes. So why I am saying this, it's a 3-byte instruction. What is the logic? How do I know? It's not written here, right? So it is written, but in a slightly different way. Look at the addressing modes, indirect and register. Indirect means basically at the rate any one of the R registers, or at the rate accumulator, or at the rate B, or whatever other SFRs. So that is basically indirect. So I can write CJNZ that particular indirect thing for 1 byte, and this immediate data is another byte, and relative is the third byte. Okay, so if it is a direct addressing mode, then this would have taken 4 bytes. Okay, if it is a direct. If it is immediate, again this byte value should be some 8-bit value. But instead, what the designers of 8051 might have thought that, so they will have multiple opcodes for this part. So there is no single opcode for this mnemonic. Mnemonic CJ, any byte is having multiple opcodes. If it is A in place of byte, there is one opcode, for B another opcode, and so on. Okay, so only there are a handful of registers which can fit over here. So that's why there are, I think, a few number of opcodes. So with around 10 or 12 opcodes possibilities are there. So here. I think okay, so maybe I'm missing some instructions. I think just a few instructions are remaining. So let me find out where I think. There is something called a call. There are different types of call instructions, and where are those? Let me see. Here. Okay, they have given it in separate chart. That's why I was unable to search. No problem. Just I think 2 or 3 instructions or 4 instructions are remaining. That's all for in the instruction set. We have covered most of them. So I told you that addressing mode 11. So to address 2 kilobytes memory space. So that is used specifically in these 2 instructions, a call and a jump instructions. So absolute call. So we have seen call instruction, right, earlier. So simple call instruction means what? It does push operation for the program counter, right? Yeah, I've said, and then it takes the role of a jump. So it updates the program counter with the 16-bit value. That was simple call address 16. Okay. So the modified call instructions are available in A call and L call format. So L call is basically similar to simple call instruction. Okay. So long call means you can address again a entire 16-bit location. It is actually same as simple call. So both the mnemonics can be interchanged over here, but A call is slightly different. A call is only having 11 bits addressing space available. So that means you can only go 2 kilobytes space. That means 1 kilobyte before and 1 kilobyte after. Okay, so within this A call, so that means you just have to apply the 11-bit address along with the absolute call instruction. Now, if you copy this code and put it in another processor or memory mapping, obviously A call instruction, L call instructions are not preferred over there. So L call and A call are present if you are good with absolute value of the address is possible to be provided and it doesn't cause any error. So A call, L call is just difference is that it's similar to call instruction, only number of bits in the address lines. Similarly, jump, which is basically doesn't save the program counter value, for L jump and A jump. So this absolute jump 11 bits address with 11-bit address and absolute jump. This L jump is actually same as A jump. Only thing is that address is 16 bits. Okay, so here no program counter is saved, and for call program counter is saved. And the very last instruction that we'll cover in this entire instruction set summary is this is jump, which is short jump. So short jump, basically we have seen JC or JNZ REL kind of instruction. So that was conditional jump instructions. Whereas is jump is unconditional jump. It's like simple jump. It's like simple JMP instruction, but only with 8-bit address, 8-bit relative address. So short means minus 128 and plus 127 and the present location where this is jump is written. So this is basically the entire instruction set for the microcontroller 8051. Okay, so this why I've spent so much time in the instruction set. First of all, CISC instruction set is slightly longer, and secondly, and more importantly rather, you must have proper grip on the functions of the instruction. So in microcontroller, essentially, I'll give you a top level summary. You have to understand what is there inside a microcontroller, basically block diagram and the pin configuration. So that is something, some hardware resources. Secondly, what are the instructions that are supported by that particular hardware? So instruction sets are always customized for the hardware in microcontrollers. For every microcontroller, you will see that there are customized or specific instructions. You cannot use 8051 instructions in ARM or other way around, ARM instructions in 8051. But the concepts are same. The concepts at the very root level are actually quite similar. There are definitely changes, as I said. There are more fancy and more effective low power and other powerful blocks which are added, but the method, how the data flows, how the read write operation happens, how memory is accessed, how basically the timing and control operates, how the instruction decoding happens, all these things are pretty similar. Pretty similar. There's lots of similarity, lots of overlap between this. So you have to understand the hardware, you have to understand the software abilities like instruction sets. Instruction sets are just the tools for writing program, as you all know. And now using both the knowledge, you have to write some code. So in embedded systems, your code should be attuned to your hardware resource. And in the process, you should think how many clock cycles you are going to utilize. Suppose I can execute L call and A call for certain location within, let's say, 1 kilobyte plus or minus from the existing location. So which one I will select? So that's a judicious decision that you must take. Okay, so I can also take any one of these to A jump, L jump, but which one? Look at this number of bytes and oscillator period. So how do I decide? The number of bytes A call takes in the program memory is 2 bytes, whereas L call is taking 3 bytes. So that means with L call, I'm going to have more number of program memory access than A call. But obviously, if my address is for wherever I'm calling the subroutine, from wherever I'm calling the subroutine is far off, obviously I have to sprint. Suppose I have to travel very far. Suppose I want to go to, let's say, from one city to another. If there is a train connectivity and which is cheaper, I will prefer train. Now my question comes whether time is more valuable or money is more valuable to me. Okay, I have to take a judicious step. So same thing here, exactly same thing here. So I can actually decide how many, whether I'm trying to save some memory or I'm trying to save some time. You will see some for certain instructions, you save some time also. Okay, so you have to keep this knowledge with you and then apply it as you go along. So let's look at a few simple programs that I've actually kept. I'll share this PPT with you. So this PPT is basically tells you about whatever we have already discussed with the instructions. So different types of operands, different types of addressing modes and so on. All instructions from this hardware manual that I have spoken to you. So that's why hardware manual I'm referring, because that's the original document that anyone should refer. Look at every instruction, read through every instruction. You don't have to remember the number of bytes or oscillator periods as such. This is not recommended, but you have to remember how the instructions are applied. So just try to practice by writing how the structure of the instructions are there, or allowed structures, because there are certain things that may not be possible. We have seen the possibilities, but we have not explored the not possibility part of it. Like, so address at RI, so you cannot give address at R3 over here, right? So that is a not possibility part. So sub B at A comma address at RI. Okay, so address at, you can take, see, look at this fine differences. I'll just highlight just one or two. So subtract with borrow A comma Rn. Rn means R0 to R7, Ri means R0 and R1 only. So at the rate, whenever you are using at the rate, that is indirect RAM addressing or indirect addressing mode, you are only allowed to use R0 and R1. Whereas while you are using registered addressing mode, you can use all R0 to R7. So these are possibilities. So, and impossibilities over here are not possibilities over here. Basically, R2 to R7 are not possible to use with at the rate signal. Okay, so these are some fine lines that you will find all over. So whenever you find at the rate some register name, that means R0 and R1. So this is something to be remembered or noted, and as you practice, it will get digested and acquired in your skills. So all instructions are given. You can see move X, move C, simple move. So mostly move instructions are commonly used, and obviously you may need move C and move X sometimes. Okay, let's look at a very simple code example. Now, in this code, in this course, for 8051 at least, we will mostly concentrate on assemblers, but at point I will give you some C examples. Now, the point is, C codes are high-level languages, and you can write a C code for a microcontroller, and the compiler will generate some code similar to the assembly code in the background, and from assembly, it will do some sort of opcode and basically those binary level binary file generation, and that binary file essentially gets stored in the program memory for execution. So essentially I'm writing everything in this code which will go to the program memory, not to the data memory. If data memory is required, we have to manage that separately, or within the program memory code we have to manage the data memory through our instructions. So assembly level instructions are more efficient than C codes. Whereas C codes are easier to write because it's a high level language. You need some knowledge about hardware, but extreme expertise may not be a necessity. Whereas for assembly code, expertise is necessity for hardware, and basically your hardware understanding should be strong enough for assembly code. Even for C embedded also that is required, but not to the extent as assembly. Now the advantage of assembly is that you can write very time efficient codes. You can write very memory efficient codes. And some modern C compilers, in fact all modern C compilers, allows you to write inline assembly with C. I will tell you with examples later on. So inline assembly with C. That means wherever you want simplicity, write your C code, and wherever you want to go with memory constraint or time constraint code, apply assembly codes in between C code inside your main C code. Okay, so those are possibilities. But in this example, I'm going to show you only assembly code. To toggle LEDs, toggle means just on off blinking LEDs, which are connected to port 1. So I'll tell you the reason why I have not selected port 0 here. So the reason behind is that one thing is definitely simplicity, and why is that simplicity comes, the answer to that, if you look at the pin diagram, port 1 is not multiplexed with anything else. So it is very simple. Whatever you read or write, it simply gets interacted. But port 0 and other three ports, actually port 0, 2 and 3, are multiplexed, and they are relatively one step complex, actually, just slightly complex, but not much. Okay, so that's the reason. And whatever we right, so I've selected port 1. So look at this block diagram. So
So,
whatever, yeah.
so I'm sorry to interrupt, but like we have a DSP class after this, so if you can like let us go, like there are only 2 minutes left. And
Yeah,
so
then,
actually, it's like it happens that he
Sir,
says,
the professor was very angry the last time.
oh, okay, no problem. So I'll release you then. I'll take the attendance and release you. We'll continue tomorrow. Who is your teacher for over there?
G Saha sir.
Oh, okay. Okay, yeah, you can leave now. I've taken your attendance, and you can stay back if you want to ask questions.
Sir, what's the DDR